We already know that within a given vector space Rn, we are able to break it up into some subspace and its orthogonal complement, and we know that the dimensions of those spaces have to add up to the dimension of the parent space. Now, what we are going to want to do as a result of that is something called an orthogonal decomposition. Now, an orthogonal decomposition is something that physics people use all the time. If I give you a vector f, you're used to taking part of it in the x direction and then part of it in the y direction. Well, we don't want to stop with just x and y. What we want to be able to do is apply it to any orthogonal directions and any orthogonal spaces. So, for example, if I've got a line, I know that in R2, its orthogonal complement has to be an orthogonal line. They have to be at a right angle. So what that means is I'm going to take some vector x, and effectively I want to shine a flashlight down so that part of my vector is in the line L, and I'm going to call that part x hat. And then I'm going to take a different flashlight and shine it in the other direction so that part of my vector here is in its orthogonal complement. So I'm going to call this vector x with the perpendicular sign. Now, I don't have to stop in R2. I can go to as many dimensions as I want. Just to illustrate it, right, if I'm in R3 here in this picture, I can take some vector that lives in R3. I'll take my flashlight and I will shine it down onto this subspace W, in this case a plane. So the shadow here is going to be x hat. It's the part of the vector in that subspace. And according to this dimension result that I have above, I should be able to then decompose this vector into a different part that lives in the orthogonal complement. So the idea here is that I can always break this up into an orthogonal decomposition. This is my proposition. I will be able to take any vector x and write it in terms of the subspace and then its orthogonal complement. We are going to assume our subspace W has an orthogonal basis. Now, in a later video, we are going to have to figure out how to get an orthogonal basis if we don't have one. It won't be a problem, but in order to do that, it's going to ironically turn out to be the case that we need some of the ideas from today. Now, note, this vector x hat has a special property. And that property here is that it's the vector in our subspace that is closest to x. Now, to try to illustrate that, I'm going to go back to this picture with the plane here. Now, this is a subspace, and if it's a subspace, it contains the zero vector. Not every vector that we ever deal with will live in that subspace, right? So here's our vector x. It certainly does not live in that subspace. I am going to talk about what I mean by the distance from x to that plane there. So if I were to kind of shine a flashlight down there, let's say that this is the vector here, x hat, and let's say that it forms a right angle there. Now, if I were to say, well, why do I have to use that as the distance? Maybe I'll use some other vector. So maybe there's some other distance that I want to talk about. So maybe there's this distance here to this vector v. So if that is some other vector in the plane, so we'll say that x hat and v are in this plane W, that thing also has a distance. So this vertical line here is going to be the length of x minus x hat. This red dotted line is going to be vector x minus v. And then in the plane here, this length right there is going to be the vector x hat minus v. Now it's getting a little bit tricky to see, but those can form a right triangle, right like this. And it's a different right triangle than the other one. And because they form a right triangle, we get Pythagorean theorem. So by the Pythagorean theorem, we will get this, that the length of x minus v squared is equal to the length of x minus x hat squared plus x minus v, x hat minus v squared. So the point of the story here is to compare this quantity, which is the distance from x to some other point in the plane, with this quantity, which is the distance from x straight down to there. And what you should be able to see is that that is greater than 0. And no matter what I choose, so for any v that isn't equal to x hat, I will find that this distance, this length, the length from x to some other point in the plane, is greater than or equal to x minus x hat. So this will always be bigger than that. The only way they will ever be equal is if v, the point in the plane, is equal to x hat. So that's what we mean by the closest. X hat is the closest vector in the subspace W to our x. So that's why we are going to focus on finding this thing x hat throughout this section and later on. So how to find this thing x hat? Let's start with the easy case first. So if I give you a line, let's say that that's my subspace. That line has to contain 0, and let's say it has a basis vector. Let's say this thing is the span of some vector w. So let's say right there is my vector w. Now, at the same time, if we are living in that space, there's an orthogonal complement. And just for the idea here, let's draw it as another line. They have to be orthogonal like that. So let's take our vector x. The point of the story here is that I want to shine a flashlight down, get this orthogonality here, and then this is going to create a vector x hat. That is the thing that we are looking for. That is the projection of x into that subspace. And at the same time, it's going to have a vector here that's in the orthogonal complement. Key idea. This x hat is some multiple of w because it's in the subspace. The other thing is that this vector x perp has to be orthogonal to the line. Now, from parallelogram rule or vector addition, that vector x perp is x minus x hat, right? You should be able to do some vector addition to figure that out. And that has to be perpendicular or orthogonal to the line. Well, that means it has to be orthogonal to the basis vector for the line. This is a multiple of that basis vector. So what we're going to find is that we'll get the following result. If I distribute the dot product, I'll get x dotted with w minus c times w dot with w is 0. And you will find that c is x dotted with w over w dotted with w. You have found a recipe for how to get the orthogonal projection. All you do is take your original vector, dot it with the basis vector, and then scale that by w dot w. This thing here is called a Fourier coefficient. If I have a larger dimensional space, so let's say I have a plane, there's w, same discussion as before. I've got a basis for the plane. Let's say it's a basis w1 and w2, and we are going to assume that it's an orthogonal basis. That's the key here. Again, don't fret about that too much. For the beginning, we will assume that we have an orthogonal basis, and then we'll figure out how to get one. I'm going to take a vector that is not in the plane. By my discussion from earlier, I know that the vector that is in the plane that is closest to it is this thing x hat. So I know that x hat lives in the plane. So that means that it has to be a linear combination of the two basis vectors in the plane. That's the key idea. Now, at the same time, there is a perpendicular or an orthogonal complement. My vector can be decomposed. It can have a component that is orthogonal to the plane, and we know that the orthogonal portion dotted with either one of the basis vectors has to be 0. Because it's orthogonal. That's what complements mean. Now, from vector addition, this is just x minus x hat dotted with b1. And from this key idea right here, I know that I will be able to write this as x subtract c1w1 plus c2w2. And when, sorry, I shouldn't call them b1 and b2, my mistake. These should be w1 and w2. Once again, orthogonality kicks in. X dotted with w1 subtract c1 w1 w1 dot product minus c2 w1 dot w2 dot product has to be 0. That's 0. I will find, no surprise, the same Fourier coefficient representation. C1 has to be x dotted with the first basis vector over the second. Now, similarly, I'm going to find that C2 is x dotted with W2, W2, W2. So that closest vector has a representation in terms of Fourier coefficients again. Remember, you know what x is. You know what the basis vectors W1, W2 are. So all of these things you can compute. It's completely possible for you to compute these. This is the projection of x onto w. Now, in general, we've got something called a projection theorem. If you take any vector x and you want to project it onto a subspace with an orthogonal basis, so let's say w has orthogonal basis, w1 down to wk, you are going to be able to write x in terms of that basis. Same idea that I went through above. And this is our projection theorem. And when you've got this projection theorem, life is nice. It's even simpler if we have an orthonormal basis. In that case, we are just going to have x dotted with u1. So let's say our orthonormal basis is u's, u for unit vector. u1 dotted with x times u1 all the way down to x dotted with uk into uk. If we define a matrix Q that holds these orthonormal vectors, we are going to find that if we were to take the transpose times x, we'll have this, and that'll form a vector with all of these dot products, which is nice. And that means that Q times QT into X will just use the definition of matrix vector product that we have talked about. And it's going to get us to the representation we want. This thing right here, Q times QT, is called the projection matrix. And it's the vector, it's the matrix that will project your vector onto the subspace you want. Now, if my subspace is just the span of a single vector, then the projection matrix just becomes U times U transpose. Let's say that I have two vectors in R2, and let's say W is the span of this vector 1, 2. So in terms of a coordinate grid, here's what we've got. So we'll take this vector U and kind of write it like that. There's U. It spans a line. We'll call that W. Now, if I give you some other vector, let's say Y is -3 and 9, that vector lives somewhere up here. So there is Y. What I would like to find is the projection of Y onto W. So if I shine my flashlight down here, this vector right there is Y hat. So I would love to know what the Y hat is. I want to know what the projection is there, and I want to find the distance from Y to this line W. Okay, so we know that Y hat is represented by this Fourier coefficient representation, right? You have the basis vector for the line. It's a U. All you need to do is compute this weight. Y dotted with U is going to end up being 15. U dotted with U is going to end up being 5. So this coefficient is going to end up giving me a 3U. So the vector in the line that is closest to my vector is this vector 3, 6. And how close is it? I would like to figure out the length of Y minus Y hat. Because if I look at my picture, that's the length of this dotted line. And in that case, this is going to be very simple to compute. It's just going to be the following. So I'm going to take Y minus Y hat is going to end up just being -6 and 3 if I subtract Y from that thing, and the length of this, -6 squared plus 3 squared, is going to end up giving me a square root of 45.